So, hello everybody and welcome to this talk about how ethical issues may lurk in without anyone noticing into your most innocent-looking database application. So a few words about me. My name is Sarah Diogera. I'm working in machine learning since 2012, and I'm currently working at a very cool company called PeopleDoc. So as Nicole said yesterday, we're working for human resources, and we have some position open, so check it out if that may interest you. And I want to point out that I have some strong interest in ethics, but I'm not an expert or anything, so this is more like a general overview of problems, and I don't have any big solution to bring to the table or something. So, ethics. Ethics is this like part of philosophy, which may seem sometimes a bit boring, but one thing all moral philosophers love to do, it's a good thought experiment. So I propose you to do that today. A thought experiment, promise, there won't be any trolley involved. So let's build an application all together using machine learning. What do we want this application to do? We want to help, So we want to help high schoolers, pupils from high school, to find the good university for them and to choose the good major. Why do we want to do that? Well, we all know that teenagers, they sometimes do things which are not really the best thing possible for them. And they also like experience. I mean, it's not their fault, and they may rely on cliché to choose their career and not on objective information. Furthermore, we have in tech and in also many other domains a problem with diversity. So, for example, there is very few women in tech, and that might be something. One of the possible causes of that is that girls may self-censor themselves with respect to choosing like so-called unfeminine majors such as computer science or math. And this field actually may be like the good choice for them and a field in which they will really thrive and bring something. So that's something we want to change. So first we want to build a database application, so we're going to need to collect some data, right? We're going to say that's pretty easy. I mean, there is really no big deal about collecting some data. It's all a fairly neutral process. So we want to measure academic performance. Okay, right, we're going to use grades. That seems pretty trivial. Well, I don't know how it is in your country. In France, it is well known that some high schools are like more strict about giving good grades than others. So maybe that's not such a fair metrics. Like if you come from this very strict high school, you get lower grades, and that doesn't really mean that you're a worse student. So maybe we should rather use like grades with a weighting scheme based on the high school level. But then if you come in a so-called low-level high school, even if you've got already the top grades possible, you will be penalized, so that's not fair to you. And maybe the real question we want to ask is, do we even want to use grades at all? As maybe we want to use also like teacher appraisal of the student work, so it's not that simple. Thing is, whenever we're collecting data, we are collecting data which are coming from our world, and our real world is like biased and prejudiced. And so we may encode some of this bias into our data sets. For example, as we said, there's fewer girls in technical studies as there are boys, so maybe the algorithm will learn that gender is a strong predictor of interest for computer science, and that's not something we want to do. You're going to say, okay, easy. You just remove all gender and other protected attributes mentioned in the data set. Yeah, but these attributes are most often redundantly encoded. For example, which studies you choose, whether you go to the university or not, it's strongly dependent of your social classes. But it's also, your social class also is correlated with which high school you went to, which option you choose in that high school, which language you learn. So not that easy. And another thing I want to point out is something that statistics call sampling bias. That is to say, some indicator may be some indicator may be not uniformly measured on the population. For example, let's say we want to, in addition to grades, we want to consider whether the pupil has taken part into an extracurricular math competition. That sounds like a great indicator to show that this person is really interested in science. Problem is, like, teachers are more likely to encourage boys than girls to take part in this competition, so that's a biased indicator of interest for science. Great, so now we've got some data, and some of them it's categorical. We've asked students about what is their dream job. So now we need to encode some text, and that's not so easy. So there is two main ways of encoding text. One of them is bag of words. Bag of words is relying on sparse encoding. Basically, it's a one-hot encoding. And you choose a vocabulary, and then you put a one if the word at the position in the vocabulary is the word, if the word is in the text. Another, maybe better way to encode text is using word embeddings, such as word2vec. This is learning dense embedding into a high-dimensional vectorial space, and the great thing about word2vec and word embedding in general is that they retain some similarity information. So for example, on bag of words, you can see that every word has the same distance from each other. And whereas for if word2vec, nurse and physician, so medical doctor, they are closer than nurse and math teacher, for example. That seems like a great thing, and furthermore, word embedding can learn analogies. That is to say, you take the vector for king, you subtract the vector for man, you add the vector for woman, and you get the vector for the word queen. So that's really great. Let's do that with job names. So you take developers, you subtract man, you add woman, what do you get? Any idea? Homemaker. Oh yeah, that's not so great, right? Thing is, it's the same problem I said before. We're learning from our data we produce in our society, so we encoded the bias in that were in our society. So Kaliskans and co-author have shown that all the bias you can find in the human population with tests such as the implicit association test can be found again in words embedding. Good news is, if you know what you're looking for and you're willing to take some time, it's possible to debias this word embedding. So for example, if we take again the gender thing, we've got brother and sister, which are gender words, and we want to keep this gender information, but all the job names, the occupations, they should be gender neutral, so we can learn this linear transformation to put that physician and nurse and computer programmers and homemaker are all on this neutral line. So now that we've got some data, it's time for a small message from the security team. And the thing is, as soon as you're handling data, and especially sensitive and private data, you become co-responsible for the security of this data. The main message is that the only data that cannot get stolen is the data you don't have. A corollary to that is if you no longer need some data, you should delete it. And I know it's like the hardest advice to follow ever, because we data scientists are big like dragons hoarding our pile of gold, like data is our treasure, we don't want to part with it, blah, blah, blah. But really, you should consider that and protect the data of the user you're handling. And if possible, you should work on anonymized data. Anonymization, there was like this tutorial 2 days ago about that. It's like a whole topic, and it's not just removing personal identifier. For example, if you take all students of a class, they're probably going to have the same age. So if you got this student, which is 2 years early or 2 years late on the curriculum, and you just keep the date of birth and the high school name in your data set, you're probably going to be able to identify uniquely this student. So it's not anonymized. So now that we've got some nice data, and of course with encrypted it and we treat it with care. It's time to go to the more machine learning part, and we're going to learn a score to predict academic success, because as we've seen, grades are not great, so we want to combine several features to do something better. The first question is, how do we, we want it to be fair, but what does it mean for an algorithm to be fair? A first answer would be, well, it should be calibrated. That is to say, if we have a certain reference score, the probability of graduating is the same for everybody, regardless of which subgroups you belong to. Here, by subgroups, I understand that might be male versus female, or that may be ethnic subgroups, or social class subgroups, or pretty much anything you can split in. So calibration is important. Then, as a university, they're going to use our score to choose which students they should accept. So they want to know if they set the score to a certain threshold and they take everybody that is above that threshold, what's the probability of them graduating? And we want this probability to be the same along all subgroups. Once again, we don't want to have a difference between, for example, white and non-white students. If you're a student, what interests you is more like the false negative rate. That is the probability that even if you would have graduated, you get a too low score to be admitted to this university. And that also, we want it to be the same on all subgroups. And another way to express that is that the average score for all students graduating is the same if you split it in different subgroups. You can do the same for false positive rates, that is, students we predicted they would graduate and they fail. And we want also to have no difference between subgroups and same average. And last, we might want to have some equal acceptance rate, that is to say that the students in the university reflect the diversity you have in the general population. So you have the same probability of being accepted regardless of which group you belong to. And at least for me, all these criteria seems quite reasonable. The problem is you can't have all of them. And it's not like wishful thinking, it's actually mathematical theorems. There's quite a lot of literature on the subject. And even if you pick only 3, it's difficult. And if you pick 2 and you add this individual fairness requirement, that is to say you can't choose the threshold based on which subgroup the student belongs to, you might not even be able to have 2 of these criteria. So really you need to choose what you talk about when you say my algorithm is fair, and you need to advertise that it's fair with respect to that metric, so that everybody knows and the shareholders know and can make informed decisions. Okay, now it's up to the fun part. We can build some models, so probably just go to deep learning. It's really hypey and everything, right? Let me tell you a story. So once upon ago, in a hospital far, far away, there was some expert who wanted to learn a predictor of whether a patient who has undergone an operation could safely go home and should stay at the hospital to be they have a high risk of complications, so it's better he or she stay at the hospital. And they learned decision trees, and it worked very well, and it was great. And so the doctor said, okay, yeah, what are the criteria that are used to determine whether a patient should go home or not? And they realized that asthmatic patients, asthma was like a predictor of low risk. And medical doctors were like, oh, that's strange, because actually asthmatic patients are really so high risk that we always kept them in intensive care units. And so as these patients were kept in intensive care units, they had a very low rate of complication. And that's what the algorithm picked up. But we definitely don't want this decision tree to go into production. So that was a good thing that it was interpretable right. A neural network, we won't have been able to pick that out. So as you've seen, interpretability can be used to debug and get feedback from domain experts. It's also in the area of ethics. It enables to make sure that decisions were made on fair ground and not use any discriminatory measure. And for example, for GDPR, there is this right to explain an explanation, that is to say you have to be able to explain how your algorithm is working. So as I said, it's a huge topic, so 3 quick points. Before building a model, you can have some interpretability using exploratory analysis, such as clustering, and all visualization techniques, so principal composite analysis, stochastic neighbor estimation. While you are building your model, you can choose to enforce interpretability. For example, so using decision trees, using everything that is rule-based, using everything that is prototype-based, such as k-nearest network, using ensuring sparsity, so that not too many of your features are coming into play. So I wanted to show quickly, because it's EuroPython, so that's a slide from the Python library called li5, so from the name explain like M5. And it's a pipeline combining bag of words and logistic regression, and words that are highlighted in greens are actually words which were the more predictive of classifying this text as medical literature. And that's a great way to check that your text model is actually learning something useful and not relying too much on noise. Last but not least, deep learning is still really useful. So you can have some interpretability after you build your model. So either building a surrogate model, which would be an interpretable model you learn on the input and output of your black box model, or doing sensitivity analysis, such as is performed by LINE, which stands for locally interpretable model agnostic explanations. And so they fit a linear model, which is a bit like a first order limited development, and so that you get an idea why this point in particular was classified as it was. Another huge subject, if you're a bit in the field of machine learning, you might know minority classes and minority subconcepts. So the problem is that the less data you have, the less accurate you are. So you can get something like that. Like if you've got really few points, it gets really messy. And the problem is we all tend to use accuracy because it's easy, it's a single measure. But you can have a very high accuracy on your majority class and then still perform very badly on your minority classes. It's not acceptable in many sensitive fields. For example, imagine a process for college application. For white students, they will really thoroughly study the application and decide. And for all other students, they just throw away all the application in the air and they pick which fall quite close. Like a random toss of a coin. You don't say, oh, no, that's not a process you want to have, so really just don't put that in your algorithm and say it's okay. It can get even worse. For example, suppose that we have, in big cities, if you are in a big high school, you have a lot of options to choose from. You can learn fancy language, so you have a higher chance of academic success. And if you're in the countryside, high school are not that fancy, and you don't have any fancy option anyway. So if you're a small high school, you have a lot of support from your teacher, and then you get better chance of success. But then if you put everything together, the minority subconcept, so what's happening in the country, it's just becoming noise for the majority classes. So you're just actually drowning out a total, so the experience of a big part, I mean, the minority, but that can be still a lot of people, it's drawn by the majority concepts. Okay, now that we've done some algorithm, we want to evaluate that. And we all do that really cleanly, so we are going to evaluate on a validation dataset, because we know that's the right thing to do. Yes, except that, yeah, our pre-processing step, or maybe our feature selection step, I was talking about that this morning. We did that on the whole data set, didn't we, right? Nah, that's not so good, right? And we had 3 algorithms, and we chose the best of 3 on our test data set, and we also presented the result on the test data set. Yeah, so that's a bit like indirect overfitting, maybe. And also we use accuracy even if we had minority classes. That's not really honest. So it's really important to be able to give an honest feedback and an honest evaluation of how good your algorithm is performing, so that stakeholders can decide with all the information whether it's okay to be put into production or not. The fact is that biases are not only in the data. We as data scientists, we are human, and doing good science is really hard, and we are subject to cognitive bias as everybody, like apophenia. So apophenia is the tendency to see patterns in noise, and for data scientists, it is not at all an occupational hazard, right? And then there is illusory causation, or confusing correlation and causality. This graph is about the number of degree awarded in civil engineering in the US and consumption of mozzarella cheese. So maybe the causality link is a bit weak. And once we find some causality, we think it happens, we tend to only notice facts which are, well, confirming what we already believe. Now, it's the good time, we're going to put our application into production. So here are some quick numbers. In 2017, the dropout ratio was 10%, the general dropout ratio, and so it was 9% for boys and 13% for girls. And the gender ratio was 3/4 to 1/4. And we want to minimize the dropout rate. So we're going to learn an algorithm, blah, blah, blah. It says, OK, there are more girls which are dropping out than boys, so probably it's like we're sending girls which are not really motivated. So let's do that and try less girls, more boys. Except that as there is even less girls, the atmosphere grew more toxic, there is more maybe sexist jokes or that kind of things. So there are even more girls which are dropping out. But since they are in the minority, the dropout rate is still decreasing, not by much, but still, at least it stays stable. And that's exactly the kind of thing that can happen with feedback loops, is that it's really easy to spin out of control, and if you're not checking the right metrics, not to even realize what is happening, and to have this self-reinforcing loops in which you are doing something you really do not want and you're doing it more and more. OK, I've got some great news, just got a phone call, and now you can deploy our algorithm to the wall of France. How cool is that, right? Yeah, except that even if we manage to get to this 99% of accuracy out of the 700,000 students which are taking their baccalaureate this year in France, that still means that we're going to get 7,000 students wrong affectation, a wrong choice of university. And that's quite a lot. And given all what we said before about minority classes and the bias toward majority in machine learning, it's probably going to be students from minority and unprivileged backgrounds. So that's really, really bad. So that's what Kefi O'Neill called a weapon of math destruction, a black box algorithm doing self-reinforcing damages in a large scale. To wrap it up, a few takeaways. First thing is that data is not neutral. Data collection, it involves a lot of conscious and unconscious choices. And these choices can be challenged, and we should challenge them. The other thing is that algorithms, they may seem objective because they're like only mathematical function and such, but actually they're learning for biased data, and they're being tuned by biased humans. So they're not fairer or more objective than humans would be. And the last thing is that, well, data scientists are only human, and we should try to keep that in mind and not feel any better, and try to improve and reduce bias in our algorithm. So that's all for me. I don't know if there's time for any questions.